Guys, so today we're gonna proceed further with our first Verilog tutorial on XILINX ISE design suite. So we'll begin from the beginning by opening the Oracle VM virtual box of an ISE design suite which we created in the last video, and this is the extension of that. So here you can see that last time we downloaded and installed the ISE 14.7 virtual machine for Windows 11 and Windows 10. So you can see this interface is now available on the VM Oracle box. So you need to click on this, and we'll see in a few minutes that our uh, window will get open. Yeah. You can close this unnecessary notification. This will take some time. And here all I would like to let you know that I have already uploaded one video of BIOS, how to enabling and disabling the BIOS. So what happens is whenever you switch off your PC, the BIOS get disabled, and many times it happens that when you click on the Oracle and when you want to code on Xilinx, you are unable to do that because the BIOS again got disabled. So as long as you are working with the Oracle virtual machine, it is recommended that before starting your project work and opening the Xilinx Windows, first initially you should begin with enabling the virtualization Hyper-V BIOS of your Windows 11 and or Windows 10. Then you start and begin to work on the Xilinx software. So here you can see that ISC 14.7 virtual machine is now running under Oracle VM box. So here you can see a project navigator. Click on this. It is getting started. Okay. Okay. We'll close this notification and maximize the size. So here you can see some previously opened file is shown over here, and it is describing some design summary of that file. But today in our first tutorial we will start with a very basic logic gates, and I will create one Verilog code for AND gate. So for that you need to go in a file, click on new project, give some name. I am giving tutorial, and here you can define the location of the your Verilog codes. I have created one folder on the desktop naming the Verilog, and in that I am creating the tutorial name project. Then go to the next. One more thing, keep this HDL. There are some more options available: HDL, schematic, ADIF, NGC, and NGO. But we are dealing with HDL codes, hardware descriptive language. So we'll select HDL only and we'll go to the next. Under this project setting, you can select which device you are selecting, you are going for to interface while implementing the Verilog code. So here we are selecting the Spartan 3 and the device is XC3S50. Then under preferred language, you can either go for VHDL and either for Verilog, but here we are going for Verilog code, so select Verilog, and the below settings need to be as it is. Then go to the next and then finish. So now you can see on the left hand side that you will find one project is created naming tutorials. Under that the device name is given for which you're gonna implement and run your output and logics after writing a proper Verilog code. So as of now, we are not connecting any device, but we'll gonna do it at a software level only. So on clicking on this file, name of this hardware, click, we're gonna create a file under this project. So click, right click, and then press a new source. In this new source, we are creating, we are working on Verilog code, so we'll click on the Verilog module, and you need to give a file name. Some constraints are there while giving a file name, that you cannot give a spacing, you cannot provide a symbol, or you should not give keywords such as or, and, XOR. These are the keywords which are the primitives and already available in the Verilog Verilog coding language. So don't use those keywords, it will not take, it will show an error. So it is better to give some random name. As we are working on AND gate, we will give the name of our file is and we'll create a two input AND gate, so we'll write it as such. So AND for two input AND gate, and click on next. Here you can define the port's name. As we already know that we will be giving a two input, so you can give here name A, and the direction of the input is input, so you will select input, and the variable B for the input pin, second pin input, and the direction is input. And if you are giving C, naming C as the output, then the direction changes to output. You can also give in out as a direction when one single variable is working as input and output also, but it rarely happens, and it happens in a very big and long codes. But we are dealing with very basic and simple code, and we know that C variable is working as an output, so we can give the name output. So here we are not dealing with the bus part and LSB and MSB bits. If you are leaving it as it is, then it is taking it by default as a 1 bit AND gate. But if you are defining some values like here, so what this is, 0 to 4 is 5 bit, 0 to 7 is 8 bit, but here we are not defining bits, we are not defining ports. So I usually don't define ports and bits over here, but it's more preferable to write in the code itself. So we'll go and click on the next and finish. Guys, this is very important tutorial because it is first tutorial and very basic one, so it is must for you to focus on the working and initial part of the Verilog language. So module end2 is the file name. We'll create a module naming end2. We'll give a name of input and output. In this first bracket, there should be a name of the inputs and outputs. So A, comma B, comma C. So these are our three inputs variable and one output variable, two input variable and two output. So now we'll define what are the inputs. So for input A, comma B are our inputs, and output is only one, that is C. Sorry, I haven't given space. See, you can see that output is a keyword and its color needs to be changed to blue, but as I hadn't given a space, it doesn't change, so it shows that yeah, it was error, but now it is not error. There's three level at which you can write a code, that is behavior level, then structure level, and gate level. So here I'm using a gate level. So in that, and is the keyword, give the name of this gate G1, and the syntax of the inside syntax should be output input input. So output is our C, then input is A, comma B. and semicolon. So this is the AND gate which is under the G1 variable. So this is our code is done. So in the implementation part, in the view you can see that is one is implementation, one is simulation. You need to select and two and see the design, utilities and design constraints. It is not required as of now, so we will synthesize our design. And it is asking, do you want to save changes? Yes. So under the synthesize, you can see that design is showing some error or not. It is showing the design summary. Okay, it was showing some error that N2 is already in design summary, so we can change the name of the module to something else. N2 to N2 1 can be taken. Again, we can save the design and synthesize. Now the warning is gone, so that I need to show you that if you take the device file name that already exists in the project library, in the tool library, then it doesn't take and it will show warning and errors. So now you can see that the synthesis of the is done, completed successfully. Now the next step is view the RTL schematic. Start with the schematic of the top level block and OK. So this is the how our AND gate looks like. So they show the interior design. When you double click on that RTL top view, you will see that the interior design of AND gate looks like as such. So there are two input variables A, B, and one is output, and under that black box, this is the design we have. So this is the zoom buttons, zoom to box, zoom in out, zoom in. So we'll do zoom to box, zoom to full view. We are clicking zoom to full view to have a complete view of your RTL, which is created by this tool. So now what we'll check the logics of this AND gate. So what is supposed to be the logic of AND gate? I will show you on here the truth table of AND gate. So you can see that if A and B both are 1, the output is supposed to be 1. If either of the one input is 0, the output goes low. And if both input are 0, then the output is low. Go back to the tool and we'll check the waveforms. So for that you need to run and translate the design into the waveform. We'll check the functionality of the code by giving the input, and we'll see whether we are getting a proper desired output or not. Okay, so for waveform and simulation of the functionality, we'll go to and here and click on simulation and then click on the file, and in iSim simulator we'll see the simulate behavioral design. We'll see the waveforms. Okay. So here we can see the navigator showing the waveforms of the input and output. So right now we haven't given any inputs and output, so that's why is showing ZZX. So at A, let's suppose we give a force constant value 1, and the value radix is binary, apply, okay. And at B, the force constant we are giving is 0 and apply, okay. And then what we'll do is we'll run this. So see what happens at 1 0, your output is supposed to be 0. So we are getting 0. So now let's change the input B to 1. Apply, OK, and run. So see at 1 1 you are getting the output as 1. Zoom to fit in full view of the waves. It shows that the first waveforms at 1 0 1 1 0 you are getting 0, at 1 1 you are getting 1. Let's suppose now B is 1 and we'll change A to 0, so force constant to 0 and apply and OK and run. So yes, we can see this also. You can see here that at 0 1 the output is 0. So here we have completely successfully implemented the AND get logic along with checking the functionality and behavioral uh, of. So in next tutorial we will see for implementation of some higher and complex gates one by one. The waveform can also be generated by creating a test bench. So we'll see that also. We'll see how to give the force clock, and all such learnings are there in the upcoming tutorials. So keep tuned, like, share, and keep learning. Stay safe, guys, and do like if you like the videos and learning part. Thank you so much. We'll meet in the next tutorial. Thank you.